Hi guys, welcome back to the channel. In the last lecture, we have discussed this problem, right? And we calculated the collapse load for this frame. Okay. And the collapse load was coming out to be 266.67 kilonewton, which is acting to the right, acting in the right direction at this point B, and which is acting downward at this point C. Okay. So these are our collapse load for this loading system, the combined mechanism was coming critical. Okay, and the combined mechanism was coming critical. Combined mechanism was coming critical. Okay, and in this problem we will be calculating the internal forces, external reaction forces, external reaction forces, and bending moment diagram at collapse. Okay, when the combined mechanism was coming critical, the plastic hinges were forming at this A point, this C point, this D point, and this E point. So 4 plastic hinges were forming in this frame, right? And the plastic hinge was not forming at this P point. That thing we have already discussed, okay, in the last lecture. So in this lecture, we are going to mainly discuss how to calculate the internal reaction forces and external reaction forces. And with the help of that, we will be drawing the bending moment diagram at the collapse. Okay. So now, when this frame in the collapse state, the deflection of this frame will look like this. Okay, and this angle will remain 90 degree because no plastic hinges is forming at this B point. This is C, this is D, this is E, this is A, right? We know that moment at this A, C, D and E is equals to MP, and the MP value is given in the question. The value is 200 kilonewton meter. This is the full plastic moment capacity of this cross section, and the cross section of all the members, this beam, this column, this beam and this column is same. So that's why the plastic moment capacity is constant, right? So now let us come to this first E point. At E, we will be calculating the reaction forces. We will be calculating reaction forces. Okay, so if you see at this E point, let us take this member DE. At this E point, right, let us assume this reaction force is acting in this left direction and the value is REH. Okay, one vertical reaction will be there because this is a fixed support, so the reaction will be REV. Okay, and one moment will also act, and the direction of the moment will be, here you can see that at this E point there is a rotation in clockwise direction. So moment will act opposite to this, and this will be MP, right? So at this point the MP value is 200 kilonewton meter. So at this E point the bending moment will act in anti-clockwise direction, and the value will be 200 kilonewton meter, right? This is E point, this is D. At the D point, you can see that the direction of the rotation of the member is in clockwise. So again, the moment will be in anti-clockwise direction. So moment will be in anti-clockwise direction. The value will be 200 kilonewton meter, right? So if you calculate summation MD equals to 0, summation MD equals to 0, and calculate this REH. So REH into 2. This distance is 2 meter. Okay, this moment is in anti-clockwise, so I will put negative sign. Clockwise moment I am considering positive in this equation, and anti-clockwise moment negative. Again this moment is anti-clockwise, so again negative, and this will be equals to 0. There will be no moment due to this force. Okay, so if you calculate REH from here, it will comes out to be 200 kilonewton. Okay, so horizontal reaction at this point is 200 kilonewton, which is acting in left direction, right? Moment at this point is basically 200 kilonewton meter, which is equals to the plastic moment capacity of this section. Okay, so this is done. Now we need to calculate what will be this REV, what will be the vertical reaction at this E point. Okay, so I'm for calculating the vertical reaction at E point, I'm cutting the section at this C. Okay, so if I'm cutting the section at this C, this right side portion will look like this. And I'm assuming this 266.6 load is acting, this whole load is acting on this portion. Okay, there will be one load from the downward. Let us suppose this load is this reaction. This is basically internal reaction force. So this is basically V, right? At this point, there is one vertical reaction REV, one horizontal reaction which is 200 kilonewton, and there is one moment which is 200 kilonewton meter. At this C point, C is a point of C. At this C, the plastic hinges are forming. So there will be the bending moment will be MP. So what will be the direction of the moment? The direction of the rotation is clockwise. The direction of the rotation is what is this? The rotation. This is clockwise rotation. Okay. And to balance this load, balance this moment, okay, the direction of the rotation is basically anti-clockwise. So direction of the moment will be clockwise, opposite to the direction of the rotation. This we have discussed in detail. Okay, so moment will act in this clockwise direction, and the value is 200 kilonewton meter. There should be no doubt in this, in the direction of the MP, right? You take always opposite to the direction of the rotation. Now, if you calculate summation MC equals to 0, this is C point. So I can write these two loads, these two moments will cancel out each other, because this is what clockwise, this is anti-clockwise. So effect of both at this point will be 0. So the moment at this C will become due to this force and this force. So I can write 200 into 2. This is clockwise, so positive, minus into REV into 2 equals to 0. So from here, REV will be equals to 200 kilonewton. So vertical reaction force at this point is coming out to be 200 kilonewton. Okay. So this is done. And this V reaction, this internal reaction V will be 66.67. How? Summation Fy0. If you put summation Fy0, so this is 200. To balance this force, we need some extra 66.67 force in upward direction. Okay. So from here you can calculate this V force, right? So this is okay. To balance this horizontal force 200 kilonewton, there will be horizontal force of 200 kilonewton meter acting in this right direction. Okay. And this is, let us suppose, B. So again 200 kilonewton force will be here in horizontal direction. To balance this 200 kilonewton force, there will be one again 200 kilonewton force will act in this direction. This is, let us suppose, this is point C, right? The horizontal reaction at A, this will also act in left direction. Okay, the direction of this horizontal force will be left, right? And the magnitude will be 66.67. How? If you calculate summation Fx0 in this whole frame, summation Fx0 for this whole frame, I can write 266.67 equals to 200 plus this RAH, horizontal reaction at H, at A, horizontal reaction at A. Okay, so the value comes out to be from here to 66.67, right? So at this point, the reaction force is acting 66.67. To balance this 66.67, there will be a horizontal force in right direction. Okay. Right. And if you join these 2 points, if you add these 2 points, there will be a net force of 266.67 kilonewton. So what I want to show from here is that due to this load, due to this 266.67, 200 is transferring to this member and 66.67 is transferring to this member. Okay, you can understand like this. Because this portion should be in equilibrium, this portion should be in equilibrium. So this 67 kilonewton load is divided into these 2 members, right? So this is okay. So we have calculated the, what you can say, the horizontal reaction at this A point and the moment at A. At A, the direction of the rotation is clockwise, so moment will be anti-clockwise and the value will be again 200 kilonewton meter. Because this is the plastic hinge. So at the plastic hinge, it will reach to full moment capacity. So this moment will be 200 kilonewton meter. Right? So what about the vertical reaction? At this point, the vertical reaction, internal reaction is 66.67. So this is 66.67. To balance this thing, 66.67 will act in this direction. Because if you join these two points, net force of 266.67 will act at this C point. Okay. The moment direction, this is 200 kilonewton meter. Okay, and here also this will act 200 kilonewton meter. Okay, so at this point, the direction of the rotation is clockwise, so moment will be anti-clockwise, right? So this is okay. Now to balance this vertical force, there will be vertical reaction generated at this A point, which will be equals to 67 kilonewton. If you consider the equilibrium of this part, this A, B, C, vertical equilibrium, right? And if you write summation Fi0, you will find that this reaction A value is coming out to be 66.67. So reaction at this A point is, vertical reaction at A point is coming out to be 66.67 kilonewton, right? So this is okay. One thing we need to calculate, what is the bending moment coming at this point B, because at point B, plastic hinge is not forming, okay? So we need to calculate the bending moment at this point B. What is the value of the bending moment coming on this point B? For this, I'm considering the equilibrium for the BC, for equilibrium for BC part, equilibrium of BC part. If you consider equilibrium of BC portion, so at BC, one force is acting in this downward direction at this C end, 66.67 kilonewton. Direction of the moment is 200 kilonewton meter, acting in anti-clockwise direction, right? So let us suppose direction of MB I'm assuming is what? Anti-clockwise, okay? So if you take summation M moment at B equals to 0. So I can write 66.67 into 2 minus 200 minus of MB equals to 0. This thing I can write, or better you can say that MBC. Okay, so this value will be 66.67 into 2 minus of 200. This value comes out to be MBC 66.67 kilonewton. Okay, and the direction will be negative. It is coming out to be negative. So the direction which we have assumed, the moment is acting opposite to this direction. Okay, so the moment will act in clockwise direction and the value will be 66.67, right? MBC. So MBC value is 66.67. MBA will be minus 66.7 because equilibrium of joint B. So if this is clockwise, this will be anti-clockwise. Okay. So moment acting at this point is 66.67 and at this point it is 66.67, right? So this is okay. Now we will be, so all the forces we have calculated, okay. At each joint we have calculated the bending moment coming at each joint, and we have also calculated the axial force and vertical axial force and shear force, basically you can say. Now we will be drawing the bending moment diagram. At C, the bending moment is looking like this. It's okay. If this is anti-clockwise, at D, there will be clockwise. This should be clockwise, right? So if you draw the bending moment diagram, bending moment diagram for these type of structure we have already discussed in slope deflection method in detail. Okay, if you have any doubt, you can refer to those lectures. Okay, so this is first draw the frame without any support, the simple geometry of frame. Okay, and I'm looking from this side. This side I'm looking. Okay, so if I'm looking from this side, this axis I'm taking positive, and towards here this is negative. Similarly, this is positive, this is negative. Okay, now before that, in simple beam we assume this direction positive, this direction negative. Okay, so what I'm assuming is that above this x, any point in this direction will be considered positive, and below this or at this point, suppose if there are 2 points A and B, according to my this sign convention, this point will consider be positive and this sign will be considered, this point will be considered negative according to this this assumption, right? So if you draw, if now you can see that moment acting at this point is 66.67, which is acting in anti-clockwise direction, right? So for the here you can see that if you assume the simple logic through which we draw bending moment diagram in beams, this direction is considered negative, right? So here also same thing I'm doing. I'll start my bending moment diagram from negative side. Okay, above this axis it will be considered positive, below this thing it will be considered negative. Okay, so this is the starting point of my bending moment diagram for this AB portion, right? And at B the moment is 66.67, right? And the direction at this point, at this point B is what? Anti-clockwise. So anti-clockwise, if you start from here, anti-clockwise moment is considered positive. So at this point the moment will start above this axis and it will look like this. So let us suppose this is negative, this is positive. Okay. Similarly, this B point, for this P, you'll assume this, you consider this direction. This clockwise direction is positive if we start from here. Okay. So again, it will start above this axis. Okay. And at C, the bending moment diagram, this direction will be considered positive, so it will move upward, and this magnitude will be 200 kilonewton, right? And at D, the direction of the moment is anti-clockwise. So if you see from here, anti-clockwise will be considered negative. If you move from this side, anti-clockwise direction will consider negative. So it will be below this axis. So this distance, this moment is 200 kilonewton meter, right? Now for this D member, the bending moment diagram at this D point is in anti-clockwise direction. So again, if you consider this assumption, this sign convention, so if you move from this side, you can say that this anti-clockwise moment will be positive. So it will be drawn above this axis. Okay, and at this C point, at this E point, the bending moment is anti-clockwise. So anti-clockwise moment will be considered negative. Okay, if you move from this direction, so anti-clockwise moment will be considered negative. So it will be drawn from this side, right? So you are just assuming the same assumption which you have assumed in the simple beam while drawing the bending moment diagram for the simple beam case. Okay, so this is our BMD, right? So at this C, this D, this E and this A point, the plastic hinges are forming. That's why the moment at this point is 200 kilonewton meter. And at B, you can see that the moment is very, very less. It is 66.67. So net moment is very, very less at B. So that's why plastic hinge is not forming at this B point, right? So guys, I have discussed this thing in detail, how to draw the bending moment diagram. So if you still have any doubt regarding this, you can write in the comment section. Okay. And one more thing, in the books, you have seen that bending moment is drawn on the compression side, bending moment is drawn on the tension side. So now this I have already told you about the deflection diagram, how this frame will deflect. Okay. So you can draw that thing, you can understand that thing, at which portion there is compression and which portion there is tension. I have detailed discussion I did in slope deflection method, right? So guys, thank you very much. We'll meet in the next lecture.